Hello, class. This is Lecture 12 of Global Climate Change. Today, we're going to be talking about different forms of energy, the way that affects CO2, some mitigation strategies regarding energy, and then also how the output, the CO2 that comes out of our energy production, like different ways that we might mitigate that. This is kind of a longer lecture, so I'm just going to kind of get right into it here. Um, So we already went over how personal vehicles account for only 10% of global greenhouse gas emissions, 17% in the United States. But the largest source of greenhouse gas emissions is going to be electric power generation. This is part of the reason why we have the Green Ninja project, because, reducing the amount of energy that you are consuming would translate to, less power generation, so less CO2 in the atmosphere. Some mitigation strategies in this sector range from carbon capture and storage to replacing fossil fuel-based energy sources with renewable sources, also just reducing actually how much energy you use altogether. So just a couple of facts here for you. I wrote them down. The U.S. power generation sources from 2013, these are the top 5. So coal is going to be 39%, natural gas would be 27%, nuclear is 19%, hydroelectric is 7%, and wind would be only 4%. Fossil fuel was going to compromise 67%, while renewables are 13.25. Now, if we contrast that or compare it with California, their power generation sources, again from 2013, natural gas would be 44.3%, hydroelectric is 9%, nuclear 8.84, wind is 8.55, and coal is 7.82. So the majority of gas or power generation is going to be through natural gas in California, which is, better than coal being the majority of it, which is the rest of the United States. So fossil fuel is going to actually be 52%, and renewables would be 27%. So California is on the right track with reducing, these how we generate power. So these power plants, right? We have electric power plants. These last for about 30 to 50 years. Okay, so that means that power plant decisions made now is going to affect emissions for decades because of the fact that they're going to hang on for a long period of time. It's not like they're going to build them today and then get rid of them in 5 years, or, they're pretty costly to build. So, even if they built them 10 years ago, they still have quite a few years left. We said that coal is going to be 39% in the U.S., okay? So about 30% of electricity generation comes from coal. 2006, China added power generating capacity equivalent to France's total electric grid. So due to the high population of China, they're just adding more and more ways to produce energy, majority being coal, because coal is going to be the cheapest way to do it. And for the same reason, India is going to be doubling their power generation capacity between 1990 and 2000. So it's a cheap way of producing energy, and when you have a massive amount of people like those two countries do, then generating power at a cheap cost, is the way to go. Now, 80% of this new capacity comes from coal. Okay, so that's how much of it we're looking at coal, which, the emission from these power plants is going to include CO2, so that's why we're looking at them so much. Now, in November of 2014, there was a landmark climate change deal between the U.S. and China. Okay, under this agreement, the United States would cut its level of carbon by 26 to 28% before 2025. China would also peak its emissions by 2030. A lot of this has actually changed with our current administration. So even though we were doing certain things in certain directions, they've kind of been rolled back a little bit. So we'll see what happens, in the year 2020 when we vote again for our next president. Now, U.S. coal use is on the decline. The amount of coal used by American power plants decreased 29% from 2007 to 2015. Again, our current administration did, basically start I want to say, being president, at 2016. So, these slides need to be updated because the thing is, it's a little bit difficult to find some of these numbers like all the way up until like current, like exactly 2018. I've been working on that actually all semester as to how I'm going to get more, current slides. But as of 2015, U.S. coal it was on the decline. We were using more renewable sources like solar, water, wind, and moving away from, coal and other types of power plants. There's also natural gas power plants. Now, there's advantages to these. They have capital costs aren't as much as coal, the high fuel efficiency, operational flexibility, rapid deployment, and also lower greenhouse gas and aerosol emissions, compared to coal, coming online at a yearly rate of 2% worldwide. So natural gas, is starting to, be on the rise. And as I said, California is at 44%. So the majority of our power actually comes from natural gas. So, that is better because there's less greenhouse and aerosol emissions, but we still have them. So share of global electricity production may increase from 20% to around 25% in 2030. So it's definitely changing, which is good. Here's going to be electricity generation from various sources. This is year 1970 to 2030. We have coal being above and, beyond all the rest of them, having natural gas and renewables, kind of head in head. Or projected to be, and it's rising, but so is coal because we have a lot of countries that are actually developing right now, and because the cheapest way of generating electricity is coal, then they'll be adding more power plants that are coal. So that's why that is projected to also increase as well. And part of the reason for this is actually population. The population of the world is projected to increase. So, we will need more energy to move people around and produce food and things like that. Okay, so part of, like I said, there's going to be, we're going to produce energy, but then the byproduct of that is going to be CO2. But there's this thing called carbon capture and storage. It's the process of capturing the waste carbon dioxide, and transporting it to a storage site, depositing it where it will not enter the atmosphere. Okay, so they're trying to figure out how can we prevent it from going in the atmosphere and putting it somewhere else. So all hydrocarbon fuels release CO2 upon combustion. Coal, natural gas, petroleum, biomass, all of these are going to release it, when it's producing energy. And there are 3 steps to the carbon capture and storage. First, they're going to capture the CO2, they're going to transport it, and then they're going to store it. So there's definitely various sources and sinks to CO2. We're going to have, or these are ways of storing it actually. So there's electricity generation, so it's going to go from there, and then it's going to be stored, or be transported to some sort of, facility, and then it'll possibly go into ocean storage. It might go to industrial use, some sort of mineral carbonation, CO2 geological storage. It could be stored underground as well. And then we have the coal kind of going into the power plants, biomass going into the power plants. We get the CO2 where it's pumped up, obviously from the ground, and it goes into these power plants along with oil too. So basically we have these coal, biomass, gas, and oil going into power generation, and then power generation is actually going to try and find other ways to put the output, where are they going to store it and move it to so it doesn't go up into the atmosphere here. So capturing the CO2 is already standard practice for several industries: natural gas, ammonia fertilizer, petroleum refineries, but no single large, which is over 500 milliwatts generated power plant currently captures CO2. So these natural gas ones and all that, they're going to, be capturing it, but the power plant, the large ones are not going to capture it. Carbon captures doubles the construction cost. These are the reasons why. And it adds 50% to the cost of electricity generation. So is not as, I want to say, beneficial for them when they're building the power plant, as well as just moving it around and trying to figure capturing it. It just kind of costs them more. Now, the proximity to the energy consumers and fuel sources largely determines the location of the new power plants, right? Obviously, they want to be near, where it needs to go. And only some facilities are in areas with ready access to storage locations. So these power plants are going to be kind of near larger cities, but because they're near larger cities, then the storage locations aren't going to be like right there. It'll be further away. So widespread adoption of CCS depends on successful transport of it from region of emissions to storage, because it's kind of got to go, quite a ways away. I don't really know where the power plants are around here, but I do know where they were, where I'm from in Omaha, Council Bluffs. It's kind of like an area there with a couple cities that are right next to each other. And the power plants are kind of like right outside on the edge of the city. So that way it's near the people, but I don't know where. Well, actually, they're coal power plants. There's one nuclear one. So I'm not sure where actually they store them. I should ask. I think I know somebody. I should ask them. Okay, so in an absence of liquid water, CO2 is non-corrosive and compatible with steel pipe, so they can kind of move it around. It has much higher density in liquid state than in gas state, so it's better for them to keep it in gas state, I guess. CO2 usually is subjected to high pressure and low temperature to force it into the liquid state. So I'm sorry, higher density. It means that they would want to keep it in the liquid state, so they kind of subject it to this high pressure to force it to liquid. Due to potential for leaks, transport facilities should be located away from densely populated areas. So that's, again, where these power plants are going to be kind of closer to these densely populated areas, but storage facilities would not be. Let me get a drink. Okay, so once it's transported, there are 4 potential methods of storage. They can put it into back into the industrial process. They convert it to mineral carbonates. They can pump it actually into the deep ocean or bury it in deep geological formations. So the first option is unlikely, so we're going to kind of go over the more latter ones. So a conversion into mineral carbonates, a natural mineral carbonation like limestone or magnesium carbonate, can be produced by a reaction between CO2 and calcium magnesium silicon oxides. So basically what they're doing is producing another mineral by combining CO2 with the calcium magnesium. This can serve as construction materials, and the process would consume 30 to 50% of the energy produced by a power plant. So it's not as cost effective for them, because obviously if they're going to be producing energy and that's what they're doing, and then they have to put most or a lot of that energy into just discarding the CO2, then they're gonna maybe try and find other ways to do it. Deep ocean storage was another one we went into. This is where we're injecting CO2 into deep ocean. It would initially reduce atmospheric concentrations, but over hundreds of years, it would make it back into the atmosphere, due to the exchange between the surface of the ocean and the atmosphere. And oceans offer long-term but not permanent storage of CO2 for that reason. So here's a graph with the CO2 concentration and the years, and they're kind of showing that all atmosphere release, would happen right about here in 2030, and then it would kind of decline, all Atlantic injection, Pacific injection. And then this is kind of different strategies, dispersing it by a ship. I like this shark right here. They got the platforms out there, in the Gulf, where they can kind of put it down and create these CO2 lakes. And then we have, something here that might have a pipe that would bring it down into the ocean, or maybe ships that might bring it out and put it down into the ocean. So it's just different ideas that they have here. Now, large-scale injection of CO2 in the ocean would influence sea life. This is the main reason, way I personally don't think it's a good idea. It can interfere with aerobic respiration. It may be toxic to certain organisms and completely change, the makeup of the ocean. Certain species might die off, and then other ones might thrive in, or vice versa. But dissolution into carbonate and biocarbonate forms would acidify seawater, so that's obviously not good for plant life either, so if we want to keep our oceans beautiful and have all the, all those sharks and, whales and different things, then it's not good to be putting, or acidifying it. And then the last one I mentioned was the burial into geological formations is currently the most practical option for long-term storage, actually. And several types of geological formations in sedimentary basins are suitable, actually, for CO2 storage. So, like depleted oil or natural gas fields, deep coal seams, saline formations. Oops, I'm trying to go the wrong way. So, these three places are going to be the geological formations that are suitable, actually, for us to put the CO2 down into and store it. I'm just going to kind of go through this real fast: emission sources and storage prospects, just so you can see it and pause it if you want to look at it a little bit more. Okay, so many aspects are at preliminary stages of development. We're getting more buy-in, and we're gaining more, momentum with the whole idea of climate change and the fact that we need to be doing something about CO2 emissions. So, it is in preliminary stages. The additional costs are definitely substantial to the power, the places that produce power. And the cost should decline over the next few decades. So the upfront cost is pretty high, and then it goes down a little bit. So now we're going to go into like different ways, like different types of power other than, the coal power and, what we can do about the CO2 emissions. But what are the other types of power that we can be using? First and foremost here is going to be nuclear power. Is often heralded as one of the best options for mitigating this greenhouse gas emissions, as a tremendous amount of energy per volume and does not release CO2 directly. But accidents have kept public uneasy. I mean, obviously we're dealing with nuclear power here, right? So we don't want any accidents with that. There was the 79 Three Mile Island meltdown, 1986 Chernobyl reactor explosion. This was due to poorly built accident. It was an accident waiting to happen. There's a 2011 Fukushima meltdown. I'm going to kind of skip over how this works because, you can read this on your own time, pause the video if you want. This is going to be kind of a longer video, so I just kind of want to keep it moving here. Power plants use energy released during nuclear fission. It converts uranium or plutonium mass into energy, and there's a large amount generated. U.S. Nuclear electric power, we are the leaders, other than France. France's kind of nuclear share is kind of a little bit less than us, but we're kind of going to be the number one users of it. There's 436 nuclear power plants under operation in 29 countries. It generates over 11% of the world's electricity. So here's our power plant locations. The nuclear, they're mainly, if you look at the Midwest right here, it's going to be mainly on the eastern side of the United States, and then like over in Europe, and then some in China, over there in Asia, Japan. How long will it last? It's known reserves of fissionable materials are adequate to supply nuclear power plants at a current rate for over 50 years. So it's quite a while. Rising prices of uranium will lead to increased exploration, new nuclear reactor technology, and fuel rod reprocessing. So basically technology, is going to make it more efficient. A typical nuclear power plant generates 106 cubic feet of waste each year. While over 99% of radioactivity is decayed over 40 years, the remainder very dangerous for thousands of years. So when waste strikes DNA, it may cause cancer. The main drawback to nuclear power is the waste. Like how long, will it take before it decays, and then what do we do with it after that? And then basically nuclear waste is currently actually stored on site, and this is a picture of a storage location for nuclear waste here. This is inside Yucca. I'm thinking this would be Mountain. Okay, so we also have other renewable energy sources. They're naturally replenished and do not emit greenhouse gases. Hydroelectric, wind, solar, geothermal, and tidal and waves. These meet about 20% of the world's electricity need, and it's projected to grow and to generate about 25 to 50% by 2030. So, here's some hydroelectric. We see, I think this is the Hoover Dam. Currently, largest renewable energy source, 15% of global electricity generation. It's responsible for large amounts of power generation in Scandinavia and Western Europe. Here's kind of like a depiction of actually how the water is going to run through it. It's going to, work with the turbine to generate the power, and then they're going to transmit it. The majority of new projects are in developing countries. Looks like China is going to be the leader on that, with Norway being the leader on the share. The benefits are highly predictable. Obviously, most rivers don't stop flowing unless there's a drought. Relatively low operating and maintenance costs for facilities, but the challenges are just very high construction costs, displacement of communities because there's these big things right around water sources, and large negative impacts on the river ecosystem. So here's kind of a picture of one of the Three Gorges Dam. Now we have wind, which is the second largest source of renewable energy worldwide. In 2004, it provided only 0.5% of global power generation. But by late 2015, 5% of global power generation came from wind. So it definitely increased exponentially, right, in just about 10 years here. USA is going to be a leader on electric power. I've seen so many of these, but maybe it's just more in the Midwest. Like near Denver, there's a huge one of these wind farms. Where else? I've seen them here in California. This one's in Hawaii. So they're all over the place. I'm sure you guys have seen one. U.S. and China are at the top of the two wind power producing countries, and Denmark generates the largest share of electricity from wind of any country. Now, wind speed increased significantly with height. So wind speeds are often higher over water than land. This is going to be the wind speed on average here. You can kind of see that the blue is going to be, where the highest. You can see right over there over the water, is going to be the highest ones here. And then obviously with height, and these are going to be the Rocky Mountains here. So this is where it's going to be the windiest. This is the number of wind turbines percentage of local energy production. So Texas is going to be, having 9,000. California having the most turbines at 11,000. So in Iowa, I've driven through Iowa, definitely seen a bunch of them. Illinois is on here, right here, and then Colorado. Colorado's on the bottom here. I was gonna say, I know I've seen them in Colorado. So it's currently about 49,000 turbines, this is as of 2015. The issue is that wind is highly variable. We get these big wind events that come through, right? And we have to be worried about fires. So it definitely isn't steadily the same at all times. Electricity demand may not coincide with strong winds. Obviously we use more electricity during the summer to power AC and also at night to power the lights. And it kills roughly about 30,000 birds each year. So birds definitely don't fare well to these wind farms. But it's very little compared to other structures and vehicles. I don't know if you guys have hit a bird before, but I've seen big semis hit them before. So, it's not as much as those. So I guess that's good for the birds. Benefits: small operating costs and fairly low maintenance costs, no greenhouse gas or aerosols directly. Remember, it's indirectly through production, and domestic source of energy. So we'll move right into solar here. Here's a nice little picture of some solar panels, which photovoltaic cells, I'm trying to say this word, converts electromagnetic radiation from sun into electricity. By mid-2015, it supplied 1% of the world's electricity, up from 0.14 in 2010. So this is another one that's kind of increasing quite a bit. So top global electricity source by 2050, which is around 16%. You can see that right around in here, which obviously is the desert, so it makes sense that that's where there would be the most. I've driven through this area right here on the way to Vegas, and there's the largest solar farm over there. They got these big mirrors, so there's definitely quite a few over there. Okay, so the reason why we're adding so many is because obviously manufacturing them has become more efficient. The average lifespan of solar panels have increased actually to 30 years, and the solar energy varies by region and time of day. So that's where we're kind of showing that. Solar energy can be inconsistent due to clouds, and the operating costs of these cells are as low as for any other energy source. So the cost of solar is plummeting. This is 2010. This is 1980. You can see it was like $18 per watt, basically, and it's gone down to about $2 to $3 in 2010. So they're definitely getting a lot more cost efficient here. And this is going to be price per watt again a little bit further in time. Looks like it's under $1 here by 2014. China is going to have the most solar, I want to say panels, with Germany being right underneath that. So we're like right here, this fourth, fifth. It doesn't have a date on this. I'm not sure exactly when this graph was created. But many countries generate over 4% of their electricity from solar panels, depending on the weather. And solar panels are flexible in their placement, so we can put them in many different areas. We can put them on the sides of buildings. We can make planes out of them. We can do all sorts of things with them. There's a plane that's actually powered by it. Okay, and high temperature solar panels use mirrors or lenses to concentrate sunlight and heat a fluid that can spin as electricity generator. So this is like what I was talking about, is actually in California. When you're driving through, there's these massive mirrors. You can just see the light shining right off of them. And then you can also have a solar chimney, which is where sunlight falling into a collector structure around the chimney heats air within it, and this results in the upward, convection, and it can drive turbines to generate electricity. We have solar heating, where space and water heating makes up over half of the energy consumed in a typical U.S. home. Sun can help with these tasks. We have geothermal energy, which is it uses the energy from our core to actually convert it into energy. The temperature warms by about 20 degrees Celsius per kilometer as one travels from the surface to the center. And the inner core of the Earth is 5,100 degrees Celsius, so it is very warm. And the U.S. is going to be the leader in geothermal. Locations of thinner crust, such as boundaries of tectonic plates, fault lines, and volcanoes, receive more heat from interior. So this would be the areas where we can actually get down to the core easier because it's not as thick. This is going to be kind of an idea as to how we actually pull, the energy out. We have these wells, that's going to basically, with a power plant here, is going to generate the power. So this is where water is pumped down a deep well. It's heated and returned to superheated water or steam, and because it's so warm, it's going to turn a turbine, and that's going to drive the generator. So the advantages is going to be economical, potential for expansion. It can operate during all hours of the day, and it's not sensitive to changes in weather. Lower greenhouse gas emissions than coal and natural gas power plants. The disadvantages is the sites suitable for location are often far from population centers, so away from where we need the power. Injection of water into wells could affect stability of surrounding geological formations. And overuse of location could cause crust to cool. Okay, so another form of energy is going to be tidal or wave, which is natural ocean movement, can also be used for energy. You can kind of see an idea here as to how it works. Oops. We have this float and a spar and an undersea substation. So this is actually a picture of one of them right here. So just to kind of give you guys an idea that it's there and available. But this is the end of the slideshow. I tried to keep it somewhat fast or quick for you guys, so it's not too long of a watch for you. We only have one more lecture until until you're done watching lectures, I guess. The final's coming up, and we're nearing the end of the semester. So, I hope you guys finish strong and you're doing well and hanging in there in your classes. So I'll see you next week.